Okay, let's unpack this. Today, we are diving into a vulnerability that has, well, it's rapidly evolved from a security disclosure into a full-blown infrastructure crisis.
It's really earned the comparisons to the original infamous Heartbleed bug.
We are talking about MongoBleed, officially tagged as CVE-2025-14847, a high-severity flaw impacting the MongoDB server.
And that comparison to Heartbleed is absolutely warranted. I mean, largely because the core mechanism is the same tragic story. A memory safety error allows unauthorized siphoning of sensitive data.
So it's an unauthenticated memory disclosure.
Exactly. It can quite literally bleed residual memory contents from affected systems. What's really chilling is that this code has been dormant. It's been living undetected in the wild for the better part of a decade.
A decade. That timeline alone is just staggering. And the immediate threat profile is extreme. We're looking at tens of thousands of databases globally at immediate risk.
And if an attacker can simply reach your MongoDB instance over the network?
They can remotely siphon highly sensitive data directly from the database memory. And here's the immediate, the scariest part. To trigger this entire data leak, they don't need a username. They don't need a password.
No authentication whatsoever.
Nothing. It happens right at the connection layer.
If we connect this to the bigger picture, it really defines an infrastructure risk where these memory safety flaws, which are, they're common, are dramatically amplified.
Amplified by what?
Well, they exist in components that handle pre-authenticated network traffic and are enabled by default settings. MongoDB, which, it aims for high performance, inadvertently created a scenario where a simple configuration choice like enabling compression opens a massive invisible hole.
So our mission today is to really understand the precise technical mechanism of how this happened. It's quite ingenious and why it was so easily exploited.
And most importantly for you, the listener, the immediate and urgent actions required to contain the systemic risk.
To truly grasp the exploit, we can't just look at it as a software glitch. We have to start with the communication fundamentals. How does MongoDB talk to the world, and why does that architecture make it vulnerable?
Right. So MongoDB operates outside the standard web request stack. It uses its own specialized TCP wire protocol.
Which is pretty standard for high-performance databases, right?
It is. They bypass the overhead of protocols like HTTP or REST in favor of raw speed and efficiency. It's all about optimizing that communication stream between the application and the database.
Right, so within that dedicated TCP connection, the messages aren't sent as simple plain text or even standard JSON. They use BSON binary JSON.
Which is essentially JSON data, but it's encoded to be more efficient in space and processing speed, specifically because it uses C data types for structural elements.
And to maximize that efficiency, requests sent over this protocol can be compressed.
Exactly. It's an optimization feature, commonly utilizing standard libraries like zlib for compression. And when this compression is used, the actual compressed request payload is wrapped inside a special container message.
The op-compressed message.
That's the one. And this wrapper, this op-compressed header, contains the single critical piece of user input that forms the basis of the entire vulnerability.
Okay, what is it?
It includes a field called uncompressed size. This field is designed to tell the server exactly how large the data payload should be after it's been decompressed. It's essentially a pre-declared contract from the client.
A contract about the resulting size of the data block.
The flaw lies precisely in the server's implementation of that zlib message decompression, specifically handled in the core source file message compressor zlib.cpp.
So it's a logic error.
It's a classic case of misplaced trust. The core issue is an improper handling of length parameter inconsistency, which, security researchers classify under CW130.
Okay, let's unpack this core logic error. Let's use that analogy we discussed, but we need to slow down the steps, because this is where a simple coding mistake leads to catastrophic memory exposure.
Right. The server is ready to accept a compressed message. The attacker sends one, but intentionally lies to the server using that uncompressed size field.
So they're manipulating that contract.
Exactly. Let's say the attacker's compressed payload contains a tiny command, maybe just 1 kilobyte, 1 KB of actual valid data.
Okay.
But the attacker sets that uncompressed size header field to be wrongfully large. Let's say 1 megabyte, 1 MB.
A huge discrepancy.
And the server, trusting this input because it hasn't verified anything yet, begins its allocation process.
So the server dutifully allocates a huge 1 MB buffer in its heap memory. It carves out this massive chunk of space, preparing for the payload it was promised. This initial allocation is critical, isn't it?
It is the moment of truth. When the system allocates this memory dynamically, using a low-level function like malloc in C++ag, it grabs that chunk of space from the general heap.
And here's the vital point, right?
Yeah.
The part you need to understand about memory safety in languages like C and C++ag.
Yes. For performance reasons, when memory is allocated, it is not typically zeroed out for security. It's not cleaned. It simply contains whatever residual data was previously stored in that exact location in the heap.
Left over from prior operations that may have already finished.
So the server allocates this 1 MB box, and 999 KBB of that box is just filled with old, forgotten data heap garbage from previous authenticated requests, config reads, session checks, you name it.
Wow.
Precisely. Now the decompression step happens. The tiny 1 KB compressed message is successfully decompressed, and it only fills the first 1 KB of that massive 1 MB buffer.
The decompression itself is successful. The data is valid.
And the server should, ideally, know that only 1 KB was used.
And here's where it gets really interesting. This is where the vulnerability actually manifests.
The critical failure. Once decompression is finished, the MongoDB server in all the vulnerable versions does not check the actual resulting size.
Which is only 1 KB.
Correct. Instead, it proceeds by trusting the original user-inputted uncompressed size of 1 MB. The server's logic proceeds as if 1 MB of valid data was just processed.
So you're left with an in-memory message structure that has 1 KB of real data.
Immediately followed by the adjacent 999 karametic country of completely unreferenced but very real heap memory garbage. And that entire faulty 1 MB buffer is now treated internally as the legitimate incoming message payload.
That is the ticking time bomb, a huge chunk of memory right next to the valid request. How does the attacker trigger the server to not only read that garbage, but also return it over the network without ever logging in?
Well, the first part, the data at risk, is astonishingly sensitive. Because this memory is resident in the database process heap, this leaked memory can expose cleartext credentials, auth keys,
Session tokens,
PII processed by recent queries, database configurations, even highly specific internal contexts like WireTiger storage engine configurations or Docker container paths. It's the highest value secrets right there for the taking.
Now for the ingenious and deeply concerning exploit delivery mechanism. The attacker needs to force the server to acknowledge that 1 MB of memory as a single readable piece of data and then ship it back.
This is where BSON structure and C language fundamentals meet. BSON relies heavily on C strings, which are null terminated.
Right. The null byte. The zero.
Think of it as the required period at the end of a sentence. The BSON deserializer, which is the code responsible for reading the incoming message, will parse character by character until it hits that mandatory null terminator.
And that signifies the end of the field or string.
So the server receives the malicious 1 MB payload, and its very first job is to parse the first field of the BSON object, which dictates the request type.
And the attacker exploits this by crafting that initial 1 KB of BSON data to contain a field name that intentionally lacks a null terminator.
They're essentially writing a sentence without a period.
Wait, so if the field name is supposed to be, say, query, but the attacker crafts it without the trailing null byte, the server starts reading QERY, and then it just keeps going.
It just keeps going. Exactly. The server starts scanning, looking desperately for that period. It reads past the real 1 KB of data, past the end of the legitimate message, and continues scanning deep into the adjacent 999 KBB of uninitialized heap garbage.
Until it finally hits the first null byte that just happens to be there from some previous operation.
That null byte could be 500 KBs away, or even the full 999 KB away. The server is forced to read off script, consuming all that residual data as if it were part of the initial command.
And here is the coup de grace.
The resulting field name, which now contains a potentially massive string like a password, 123 apk josa host, internal dbo01, is almost certainly invalid.
Because it's not a legal BSON field identifier.
So the server then responds with an error message, trying to be helpful by echoing the malformed string back to the client to explain the parser failure.
The error message is the leak channel. It returns something like, amble BSON field name a password, 1223 apk, handing the attacker the secrets they just found in the memory garbage.
It's an information disclosure vulnerability that relies entirely on the server failing securely. Instead of failing gracefully and sanitizing the response, the server returns the entire now leaked garbage-filled string.
And this all happens before login checks.
All of it. From allocation to error response, it happens during the connection setup. The low barrier is absolute. Any remote actor who can initiate a TCP connection can trigger this process repeatedly.
Wait, I need to pause on that scale element. If this entire process only leaks the memory resident at that exact moment in that specific 1DB chunk, how does the attacker get all the secrets?
Ah, that's where the high-velocity scraping comes in. Because the exploit is unauthenticated and extremely simple to automate, the attacker doesn't send one request.
They send thousands.
Tens of thousands in rapid succession. Each new request triggers a new memory allocation, potentially grabbing a different segment of the heap, exposing a different chunk of residual data.
So by rapidly establishing and tearing down connections, they can effectively churn the heap memory and sample enough data to harvest all the high-value secrets.
Precisely.
We've established the terrifying elegance of the exploit itself. But let's move beyond the lab and look at the sheer geography of this failure. Where are these vulnerable targets actually sitting, and how long has this been a problem?
The scope is immense. It's driven by the popularity of MongoDB and, frankly, historical poor operational security practices. According to Shodan, there are currently over 200,000 MongoDB instances directly exposed to the public internet.
200,000 instances, visible to anyone with basic scanning tools. And of those, how many have been confirmed as potentially vulnerable?
Research estimates suggest that over 87,000 MongoDB servers globally may be vulnerable. This number reflects instances running versions within the vulnerable range or those that haven't taken the necessary mitigation steps.
But these aren't just isolated sandbox environments, right? This is production infrastructure.
Absolutely. The concentrations are highest in major technology hubs. We see the highest observed exposure in the United States with about 20,000 instances.
Okay.
China is next with 17,000 instances and Germany with nearly 8,000. But really, the exposure is truly global. It just reflects MongoDB's widespread adoption.
Given that MongoDB is a foundational component of so many modern containerized cloud-native applications, what does this look like in the cloud environment specifically?
Cloud telemetry indicates that roughly 42% of observed cloud environments had at least one vulnerable MongoDB instance present.
42%.
And that percentage is crucial because it shows that organizations leveraging automated deployment methods, which often prioritize easy access and performance, are just as susceptible as those running older self-hosted deployments.
The narrative of this vulnerability is uniquely frustrating because of its age. This wasn't a flaw introduced by a rushed patch last week. It's an 8-year-old flaw.
The initial code commit that introduced this specific length-checking error occurred in May 2017.
2017.
That means instances have been vulnerable for nearly a decade. They've existed through major technology shifts, multiple corporate environments, countless security reviews, all without being detected. This longevity is why the potential historical exposure is so concerning.
We have to assume that sophisticated, persistent threat actors likely discovered and leveraged this privately long before the public disclosure in late 2025.
Absolutely. If an attacker was exploiting this discreetly 5 years ago, what does that mean for organizations who believed they were compliant and secure back then? It means that compliance, in this context, offers no protection against historical data loss.
Any sensitive data that was resident in memory during those 8 years, even if subsequently rotated, might have been leaked.
The current patching fixes the future leak, but the historical data exposure window is massive. It could stretch all the way back to 2017.
Let's talk about the remediation debt. This vulnerability affects virtually every single MongoDB release from the last decade. Can you walk us through the scope of the affected versions?
This is where the operational complexity spikes. MongoDB had to backport the fix across 6 actively supported branches. So users need to upgrade to the designated fix versions, 8.2.3, 8.0.17, 7.0.28, 6.0.27, 5.0.32, or 4.4.30.
That's a lot of versions.
The fix itself was relatively small, a check of the actual decompressed size against the promise size. But the deployment challenge is huge due to that wide version spread.
And this brings us to what you call the legacy debt crisis this vulnerability creates. What about the older end-of-life versions?
This is a major operational risk. All MongoDB Server 4.2.x, 4.0.x, and 3.6.x versions are vulnerable, and because they are officially end-of-life,
they will not receive official patches.
Correct. This leaves organizations running these legacy systems in an extremely precarious position. They cannot fix the vulnerability with a standard upgrade.
So if you're running 4.2, you have 2 unpalatable choices. Either migrate away from that system immediately, which can be a massive project,
or rely permanently on the workaround, which requires disabling a performance feature.
And that's a critical operational trade-off. Disabling compression entirely while it secures the system introduces network latency and increased bandwidth use.
especially if the legacy application relies heavily on large data transfers. Furthermore, security teams need to ensure that the setting is correctly deployed across all environments and that future configuration updates don't accidentally re-enable zlib.
Relying on a workaround for an EOL system is a high-risk posture.
It has to be treated as a temporary stopgap until retirement.
Let's look at the timeline from disclosure to active threat. MongoDB issued its security advisory on December 19, 2025. How quickly did this escalate?
The timeline was explosive. It moved from a theoretical vulnerability to an immediate emergency within a week. The critical inflection point occurred on December 25th.
Christmas Day?
Yes. A public proof of concept, a POC, exploit code was released on GitHub. This immediately democratized the attack capability. Before the POC, an attacker needed advanced knowledge. Afterward, they just needed to download a script.
And what was the industry's response in terms of observed attacks?
Active exploitation attempts targeting exposed servers were observed in the wild almost immediately following that POC release.
So threat actors are on it.
Both automated bots and human operators. They're keenly aware of the vulnerability and are attempting to scrape memory from as many vulnerable instances as possible before that patching window closes.
When we talk about severity, the security industry uses various scoring metrics. How did MongoBleed rate across the CVSS spectrum?
It landed solidly in the high to critical risk category. The CVSS V3 score places it at 7.5, which is high.
Okay.
The newer, more comprehensive CVSS V4.0 score pushes it even higher at 8.7. This high score reflects the low attack complexity and the complete lack of required user interaction or authentication.
And we also saw the BitSite DVE score, which takes into account real-world factors like active exploitation.
Yes. The DVE score was 9.71, signaling extreme risk. That score is a clear warning to practitioners. A 9.71 tells you this vulnerability is not theoretical. It is a proven, currently utilized attack vector.
The immediate data leak is obviously devastating, but when we look at infrastructure flaws like this, the real danger is always the second act, what attackers can do once they've gained that initial secret.
Absolutely. The confirmed exploitation outcome is the remote, unauthenticated disclosure of uninitialized heap memory. But that memory is a goldmine of high-value secrets. It contains the keys to the entire kingdom.
Let's zoom in on those specific high-value secrets. What is an attacker most likely to harvest and weaponize?
We're talking about cleartext database credentials, usernames, and passwords for the database itself. If the attacker gets these, they bypass any superficial network protection and gain full read-write access.
And even more critically,
They often harvest cloud access keys, like AWS secret keys or authentication tokens used by microservices connecting to MongoDB.
and once an attacker has an AWS key, even if it's scoped for just the database role, that single key suddenly transforms into a vector for a far more dangerous lateral attack.
That is the critical threat multiplier. These leaked secrets facilitate follow-on compromise and privilege escalation. An attacker can take a valid AWS key, use it to access the AWS console or API, and begin resource enumeration.
Mapping out the environment, identifying other connected databases, S3 buckets.
Or application secrets stored elsewhere. They can use the key to pivot laterally within the network, potentially compromising associated cloud infrastructure or third-party services that trust that identity.
So, the MongoDB server leak is not the end of the attack, but merely the sophisticated phishing trip that secures the highest value credentials needed for a deeper intrusion.
Precisely. The low complexity and unauthenticated nature of MongoBleed mean attackers can easily automate this scraping process at massive scale. It is the perfect mechanism for fueling sophisticated, multi-stage attacks.
Whenever a major vulnerability drops, we inevitably see initial confusion. Was there any speculation about MongoBleed's true impact?
There was significant initial speculation. Many initial reports mentioned the potential for remote code execution, or RCE.
The ultimate goal for any attacker.
Right. And the mechanism of controlling a large buffer and overwriting adjacent data often suggests RCE potential. However, both MongoDB and definitive security analysis confirmed that CVE-2025-14847 is not officially confirmed as an RCE vulnerability.
So the confirmed impact remains remote, pre-authenticated memory disclosure.
It does, and that's catastrophic enough. As we mentioned, it is classified as an improper handling of length parameter inconsistency, CVE-130. It's a very common class of memory safety flaw.
And it stems from a basic failure in input validation.
The server blindly trusts a length parameter supplied by an untrusted user, which leads to a massive uninitialized buffer overread.
This vulnerability feels like a security failure amplified by operational negligence. It reinforces just how often basic perimeter assumptions are wrong.
It forces a hard look at modern infrastructure. Memory safety flaws are common. What makes MongoBleed devastating is that it was amplified by two operational factors.
First, zlib compression, the trigger, is often enabled by default.
And second, the unacceptable number of instances, over 200,000, that are publicly exposed to the internet.
That sentiment we saw, "you deserved it if you exposed your DB to the wild," sounds harsh, but it reflects the accepted wisdom that databases should never be publicly exposed. Is there any legitimate non-negligent scenario where that might happen?
That's a fair challenge. While direct public exposure is almost always bad practice, we have to remember the rise of microservices and complex cloud architectures.
So a misconfigured networking rule or load balancer?
Exactly. Or, more commonly, developers stand up databases in non-production environments, staging, testing, QA with minimal security, forgetting that those environments are still internet accessible.
This vulnerability proves that even if you think you have perimeter defenses, the moment the network protocol is accessible, the attacker is at the gate.
Absolutely. Zero trust must be applied to the data layer. The principle of continuous verification and minimizing implicit trust must mean that even internally, you should never assume an attacker can't reach the network protocol layer.
The database must be managed as a high-priority active attack surface.
Yes, it requires segmentation, robust network controls, and aggressive continuous auditing.
We've established the depth of the problem. Now we pivot to the practical and actionable steps. For every organization running MongoDB, this section is critical. What is the single most urgent, immediate action?
The urgent action is a full immediate upgrade. You must move to the fixed supported versions released by MongoDB: 8.2.3, 8.0.17, 7.0.27, 5.0.32, or 4.4.30.
Applying these patches is the definitive, long-term fix.
It is. It corrects the logic error in the zlib decompression routine that caused the buffer miscalculation.
However, patching takes time. And as we discussed, many organizations are running EOL versions 4.2, 4.0, 3.6 that will never get a patch. Is there a temporary solution that acts as a firebreak?
Yes, there is a crucial and highly effective workaround that must be implemented immediately if patching is delayed or impossible.
Which is?
Since the vulnerability is tied specifically and exclusively to the zlib compression implementation, you can simply disable zlib compression entirely.
How is that done at a technical level?
You start the MongoD server or Mongo's router process with the configuration option network message compressors, or net.compression.compressors configured to explicitly omit zlib.
For example, you might set it to snappy stickd.
Or if you need to fully secure a legacy EOL instance, you would set it to disabled. This effectively routes traffic around the vulnerable code path, neutralizing the exploit regardless of the version you are running.
But relying on that workaround introduces the performance cost we mentioned and potentially operational risk if that setting isn't enforced globally.
That is the trade-off. For EOL versions, it is mandatory, but it's a temporary measure. For supported versions, patching is always the required path.
And once patching is complete or the workaround is successfully implemented across all environments, what is the critical secondary step that cannot be skipped?
You must immediately and comprehensively rotate all database credentials, authentication tokens, and sensitive secrets that may have been resident in memory and potentially exposed prior to the fix.
So application user passwords, admin accounts,
And especially any leaked AWS keys or API tokens. Patching stops future leaks, but rotation is the only way to mitigate the enormous risk of historical exposure over the last 8 years.
Looking forward, how do organizations change their posture to prevent this scale of risk from ever resurfacing?
The primary line of defense is network restriction. The fundamental error here was network reachability. You have to move beyond the common, unacceptable practice of public exposure.
Place all MongoDB instances on private networks.
Limit access strictly to trusted application servers using least privilege IP ranges, and implement robust egress filtering. The goal is to make the database process unreachable to any unverified external entity.
And for those services that absolutely must communicate, what about the security best practices that supplement firewalling?
Enforce strict security best practices across the board. Enforce authentication and strong role-based access control, or RBAC.
Even though authentication doesn't stop this specific pre-auth like
Right, but it limits the blast radius should credentials be leaked and used for post-leak lateral movement, and crucially, enforce TLS encryption.
And to be clear, TLS does not prevent the exploit.
No, the server still processes the malformed compressed message internally, but it ensures that if any other memory safety flaw existed that didn't trigger an error response, the attacker wouldn't be able to sniff or view the payload content in transit.
Now, we touched on the difficulty of finding all these exposed instances. In large, fragmented enterprise environments, locating shadow IT, or forgotten dev test databases, is often non-trivial.
That is the silent killer. Attackers know that the most valuable targets are often the internal databases, the legacy apps or forgotten cloud experiments that lack the hardening applied to core production systems. Comprehensive asset inventory and continuous discovery are non-negotiable.
Let's talk about detection. For security operations teams actively hunting for signs of compromise, what does exploitation look like on the network and in the logs?
First, we need to recognize the limitations of traditional monitoring. MongoDB can run on non-standard ports like 27018, 27019, or arbitrary high ports in cloud environments.
So relying solely on port 27017 is insufficient.
Absolutely. Detection must focus on behavioral analysis and protocol identification, ignoring the port number.
But what if the traffic is encrypted? If TLS 1.3 is enabled, the handshake and payload content are hidden. How do security teams hunt something they can't see?
This is where advanced detection using TLS fingerprinting becomes essential. We rely on metadata, specifically technologies like JA3S and JA4S.
The server-side counterparts to client fingerprints.
Exactly. They do not decrypt the data. Instead, they capture the specific combination and sequence of cipher suites, elliptic curves, and extensions that the MongoDB server presents during the initial TLS handshake.
So even if the payload is encrypted, the software's unique way of speaking during the handshake remains visible.
Precisely. This unique dialect of the handshake results in a hash, the JA3S or JA4S fingerprint. And because these fingerprints are highly consistent across MongoDB versions, they allow a security team to reliably identify and fingerprint MongoDB services, even on non-standard ports.
That's incredibly granular network hunting.
Yeah.
Beyond the network, what forensic footprints do these exploitation attempts leave in the database server logs?
Attack attempts leave two distinct high-fidelity footprints that every security team should be searching for right now. The first is high-velocity bursts. Legitimate production traffic generates low, steady connection rates. To effectively scrape memory, attackers must rapidly establish and tear down tens of thousands of short-lived connections.
You mentioned an astonishing number previously, 111,000 connections per minute.
Yes. Forensic analysis observed attack velocities exceeding 111,000 connections per minute against exposed servers. In contrast, legitimate application traffic typically runs at, 0.2 to 3.2 connections per minute. A sudden massive spike is a huge signature.
And what is the second indicator that differentiates an exploit attempt from a legitimate client connection?
The second indicator is the absence of client metadata. Legitimate MongoDB drivers, whether it's Node.js, PyMongo, or others, automatically send a detailed client metadata handshake immediately after connecting.
Identifying the client type, version, OS.
Right, and this corresponds to server log event ID 51800.
But the MongoBleed exploit isn't a legitimate driver. It's a specially crafted payload.
Precisely. The exploit tool connects, which is event ID 22943, and disconnects, event ID 22944, without ever sending this client metadata. Therefore, a metadata rate of 0% across a high volume of connections is the highest fidelity indicator that the connections were exploit attempts.
So security teams need to query their logging systems for these high-volume bursts that lack that expected 51800 metadata event.
Yes. That analysis is crucial for determining if and when data was exfiltrated prior to the patch.
This has been a deeply detailed and alarming deep dive into MongoBleed, CVE 2025-14847. We've unpacked the mechanism.
A simple 8-year-old memory safety error introduced in 2017.
And then forcing the BSON parser to read adjacent heap garbage via a missing null terminator.
The consequences are severe remote, unauthenticated disclosure of credentials, API keys, and sensitive PII from tens of thousands of globally exposed servers. For immediate mitigation, the paths are crystal clear.
Upgrade immediately to a patched version.
Or implement the critical workaround by disabling zlib compression via server configuration, especially for those legacy EOL versions that will never be patched.
Ultimately, the visibility challenge remains paramount. As you heard in our discussion on detection, if you can't definitively answer where every MongoDB instance is running in your environment, who can reach it? and who is touching it now.
And whether those connections exhibit the telltale behavioral anomalies.
Patching alone is insufficient.
Yeah.
You need that deep network and behavioral visibility to manage this systemic risk effectively.
This brings us to our final provocative thought for you to consider. The exploitation of MongoBleed was incredibly simple, lived in the code for nearly 8 years, and was triggered by a common network compression feature enabled by default. We discuss how this vulnerability is rooted in fundamental memory safety flaws, CVE-130, common to C and C++ development. Given the widespread use of these compression libraries, zlib, snappy, zstd across modern operating systems, virtualization platforms, application frameworks, and core infrastructure components, what other 8-year-old memory safety flaws might be lurking, waiting for a simple pre-authenticated length field mismatch to trigger a massive automated data leak? It's a question that demands continuous vigilance over the most basic yet most critical lines of code that govern modern digital life.